This tutorial corresponds to the Unit 6 notes for chemistry, Introduction to Bonding. In the previous unit, we talked about how valence electrons can be lost or gained to make an atom more stable, and that noble gases are stable with 8 valence electrons. In this unit, we'll talk specifically about what happens when the atoms gain or lose valence electrons, or even when they share them. I would suggest before going into this next part that you might pause and read through that first fill in the blank section and see what you can fill in by yourself. Okay, so the way in which the atoms of different elements bonds together depends on their outer electrons or their valence electrons. Remember, those are the electrons in the highest quantum energy level. According to the octet rule, atoms will gain, lose, or share electrons to have 8 in their outermost level. Atoms can bond by sharing their electrons to make covalent compounds, or they may form ions which bond to make ionic compounds. So if the atom is gaining or losing and forming an ion, that's going to become part of an ionic compound. One cation will bond with one anion. But if the electrons are going to be shared, which would only be done through nonmetals, it's going to be covalent. So metals generally have 1 to 4 valence electrons and will lose them to form cations. Therefore, metals are generally found only in ionic compounds. Nonmetals, however, are more versatile. They have 4 to 8 valence electrons. The ones that have 8 are called the noble gases. They generally do not become part of compounds. Other nonmetals will frequently gain electrons to become anions, which are found in ionic compounds, or sometimes nonmetals will share their electrons and become part of covalent compounds. Again, notice it takes a cation and an anion to make an ionic compound, so a metal and a nonmetal. For covalent compounds, there's only going to be nonmetals because these are ones that can share their electrons, and they don't want to share unless they have 4 to 7. Also from the last unit, we've already talked about electron dot structures or Lewis dot structures. When we do electron dot structures, we want to use the amount of valence electrons. Make sure that you know for the S and P blocks how many valence electrons each group has. If you recall, the alkali metals and hydrogen have 1 valence electron. That's because all of their electron configurations end in S1. Alkaline earth metals have 2 valence electrons. If we come over here to the P block, boron, aluminum have 3, carbon has 4, nitrogen has 5, 6, 7, and of course noble gases have 8 because they're stable. So when we do a Lewis dot diagram, we just want to use 1 dot to represent each valence electron. Since sodium is an alkali metal, it gets 1 dot. It doesn't really matter where I put it, although as we do more electron dot structures for full compounds, it'll start to make sense where we might want to put that dot. Calcium has 2 because it is an alkaline earth metal. Aluminum has 3 because it's that first column in the P block. And there's no big surprises here. I put them in order. Carbon has 4, phosphorus 5, sulfur 6, chlorine 7, and as a noble gas, neon has 8. So now we're going to start with some bonding. We're going to start with ionic. Binary ionic compounds just means that it's an ionic compound with 2 elements, or 2 types of atoms. They're made up of a positive cation, which comes as a metal loses its valence electrons, and a negative anion, which forms as a nonmetal gains electrons. There's an exchange of electrons to form this type of bond, or a lot of times you'll hear me use the word transfer of electrons. The metal transfers its electrons to the nonmetal. Ionic bonds are formed from ions. Each ion has what we call an oxidation number associated with it, indicating how many electrons it is likely to gain or lose. The oxidation number really is the same thing as the charge that we talked about in the last unit. So if you recall, alkali metals have 1 valence electron, which they lose to become a positive 1 charged ion. Alkaline earth metals lose their 2 valence electrons and become positive 2. Over here we have positive 3. As they get closer to 8 valence electrons, if they have 5 valence electrons, they gain 3 negatives to become a negative 3 charge, negative 2, negative 1, and of course noble gases do not have a charge, so their oxidation number is 0. Let's move on to how to do an electron dot structure for an ionic compound. So sodium as an alkali metal has 1 dot because it has 1 valence electron. Chlorine is a halogen, so how many dots will it get? Chlorine has 7. Now, remember that 1 to 3 valence electrons means that the atom wants to lose valence electrons, and when they have 5 to 7, they want to gain. So the same valence electron that sodium wants to lose, chlorine is willing to take. What's going to happen is a transfer of electrons. We show this by an arrow. So sodium gives its valence electron or transfers it to the chlorine ion. So you can see it goes in one direction from sodium to chlorine. A lot of times I'll use the term dot to empty spot, because if you look at chlorine, 1, 2, 3, 4, 5, 6, 7, now this is its 8th one. So it went from the dot to the empty spot on chlorine. Now, notice chlorine now has 8. Sodium really does too, we just don't see it because it's lost that highest quantum energy level. The next example is with calcium and oxygen. Calcium starts with 2, oxygen starts with 6. So you can probably guess that since calcium wants to lose 2, oxygen wants to gain 2, calcium is going to transfer its 2 valence electrons to oxygen. Again, we're going to go dot to empty spot. So calcium is going to give to oxygen. Can you see how I'm arranging my dots? With this one from sodium, I pointed it toward chlorine, and I left chlorine's empty spot pointing towards sodium. Similarly with calcium and oxygen. I put the ones that calcium wanted to give away pointing near oxygen, and I left empty spots on oxygen where it would be receiving one from calcium. Aluminum and nitrogen are going to behave in the same type of manner. Well, aluminum has 3, nitrogen has 5, so it needs 3 more to get up to 8. So aluminum transfers its 3 to nitrogen to give it 6, 7, 8. It's not always quite that simple. For example, sodium has 1 valence electron and nitrogen has 5. So of course, sodium can only give nitrogen 1, but how many does nitrogen need? Well, if it gives 1, nitrogen now has 1, 2, 3, 4, 5, 6. How will it get 2 more? So a lot of times students think, well, it needs maybe something that has more electrons. But this compound only gets to have sodium atoms and nitrogen atoms in it. So what happens is you need more sodiums to be able to give nitrogen all the electrons that it needs. So we add 1 more sodium, nitrogen's now at 7, and we add a 3rd sodium, nitrogen's now at 8. So instead of it being like those previous examples where 1 cation had the right amount of valence electrons to give to the anion, this time we need 3 atoms of the same cation to be able to give all 3 valence electrons that the anion needed. When we write the chemical formula, it's Na3 because there's 3 sodiums, N because there's only 1 nitrogen. We never have to write a 1. If there's only 1 atom in a compound, it's known to be 1. By the way, let's put this in perspective. We've been talking about compounds. Compounds are extremely small. If you recall, when we talked about copper atoms, you could line up 100 million copper atoms along a single centimeter line. Well, these aren't much bigger because we just have 4 atoms in this compound. So when we're really talking about how much there is, we're really not talking about there's only 3 sodium atoms and 1 nitrogen. That's just the ratio. There's actually billions of these going on in any kind of a sample that we could actually see. So going back a little, here we have sodium chloride, NaCl. It's 1 sodium, 1 chlorine. Similarly, calcium oxide is 1 calcium, 1 oxygen. And aluminum nitride is 1 aluminum, 1 nitrogen. So we have this 3 here. This is called a subscript to indicate that there were 3 sodiums, whereas the rest of them were just 1-to-1 ratios. Let's look at another one that's not a 1-to-1 ratio. Aluminum and chlorine. Aluminum has 3 valence electrons and chlorine has 7. Aluminum needs to get rid of all 3 of its valence electrons, but chlorine can only take 1 more to get up to 8 and reach the octet rule. So aluminum will give it to the chlorine, but what do you think happens next? Well, we need 2 more chlorines because each of those valence electrons from aluminum has to go somewhere. So we can see that aluminum gives 1 valence electron to the first chlorine, 1 to the second, and the last one to the third one. So our formula is AlCl3 because this time we needed 3 chlorines for the 1 aluminum. Even a little bit more complicated is aluminum and oxygen. Aluminum has 3 and oxygen has 6. So aluminum can give 2 of its valence electrons to this oxygen, but it still has another one that it needs to get rid of. You might want to pause and see if you can figure this out for yourself. Okay, so if I add an oxygen, then aluminum can give its last valence electron to that oxygen. However, oxygen only has 7 now, and it needs another one. Well, let's add another aluminum then. So if I add that next aluminum, it can give oxygen its second electron, but now aluminum still has 2 more to go. Okay, so let's add 1 more oxygen, and aluminum can give its last 2 electrons to that oxygen, to that last one. So the formula for this one is going to be Al2O3. Al2O3. So there are properties that ionic bonds follow. Most ionic compounds are crystalline solids at room temperature. Did you notice that first one was salt, NaCl, just plain table salt? If you think of table salt, think about it kind of in a crystal-like manner. That's because the ions are arranged in 3-dimensional patterns. Also, the individual units of an ionic compound are called formula units. That's kind of like saying the individual units of atoms are called elements. Those are kind of analogous terms. And also, when melted or dissolved in water, ionic compounds carry an electrical current. So if you think about it, when they dissolve in water, they're going to dissolve as their ions, the positives and the negatives. So there's this charge where it can carry an electrical current. So those are some properties of ionic bonds. Now we're going to do a little bit of practice on the electron dot structures before moving on to covalent.